thing we have to talk about here is how free energy relates to equilibrium. Okay? And this is going to hopefully enlighten us on a couple of issues that we've had so far with some of the practice problems. Here's the thing. The delta G we've been talking about for the most part, it's kind of been both. And we didn't really distinguish between the two until now. Delta G0 is the delta G, the free energy change at standard conditions. Okay? Now, there are a few things that standard conditions actually means. Do we remember what any of those things actually mean? Like when I put that little degree sign there. Okay, it's 1 atmosphere pressure if we're talking about gases, right? What else? It's 298 K. What else is standard conditions? Or 25 Celsius, same thing. If we're working with a solution, what's a standard concentration? Any guesses? Well, that's a volume, right? So we may not have talked too much about this. 1 molar. Okay? Now this is going to come up again when we talk about electrochem in the next unit. But a 1 molar concentration is a standard concentration. And then what am I missing here?
Greg Schrader, if you're in the building, please call Mr. Schrader's office, 26227.
Where is it? Table 19.3. Oh, okay, it was a... Okay, if it's a solid or a liquid, it's just pure solid, pure liquid. Okay, that's your standard conditions there.
Lori Jones, your visitor, is in the activities office.
Okay, yeah. So on page 822 in the book, that's where it talks about the different conventions used when we're talking about standard delta G, so delta G0. So you've got a pure solid, pure liquid, 1 atmosphere pressure, 1 molar concentration. And then if you have an element, any element, H2, N2, just iron, that sort of thing, that's all, the standard free energy is 0 for all of those things, right? Standard free energy change. So the delta G of formation for all of those is 0, okay? So those are kind of the standard conditions we have defined, okay? So the thing is, the delta G that we've talked about, when I've told you that at equilibrium, delta G equals 0, that's not delta G at standard conditions most of the time. Okay, every once in a while they can be the same. But usually, when your delta G is 0 at equilibrium, that doesn't mean your delta G0 is 0 at equilibrium. Okay, and hopefully, we'll go over a couple examples, and hopefully this will start to make a little more sense. Oops, sorry. So this equation actually relates delta G and delta G0. You've got this expression RT ln Q that can help you relate the two of them. All right, and Q, do you guys remember what Q is? Yeah, it's kind of products over reactants when we're not necessarily at equilibrium, okay? So that's your Q value. Under standard conditions, all the concentrations are 1 molar. If we're talking about concentration, all the pressures are 1 atmosphere, if we have standard conditions. So then products over reactants is just going to give you a value of 1 for Q. Natural log of 1 is 0. So this whole term goes away. I guess I should have crossed that out, not circled it. And then under standard conditions, delta G equals delta G0, okay? But if we're not at standard conditions, if your concentrations are different than 1 molar, if your pressures are different than 1 atmosphere, then we're not at standard conditions. And most of the time, we're not doing reactions under standard conditions, right? Because most of the time, you don't have an exact concentration of 1 molar. Or you don't have an exact concentration of 1, or pressure of 1 atmosphere, okay? All right, so here is an example. And I just typed these up, so I didn't take a lot of time to pay attention to whether they're relevant or not. So let me just take a look at this for a second. Chemical equation that defines the normal boiling point of liquid carbon tetrachloride. Okay, so this starts off a little weird here. You guys remember what normal boiling point means? What's that? It's when it becomes a gas, right? But the normal part. Do you remember what the normal part means? Yeah, and it's actually at, well, specifically at 1 atmosphere of pressure, okay? So CCl4, and if it's at the boiling point, then, oops, I should probably put my states of matter here. Liquid is actually in equilibrium at that moment with CCl4 gas, right? Because we are at the boiling point. So at that moment, this is a reversible reaction where it can go either direction. We're at equilibrium. And so right here, this is a pressure of 1 atmosphere, right? Okay, because for something to boil, it has to overcome atmospheric pressure. So it has to have a pressure of 1 atmosphere in order to escape from the 1 atmospheric pressure that's pushing down on it. Does that make sense? So that's at that exact moment, that's equilibrium. Okay. Now, 1 atmosphere of pressure, we're under standard conditions here, right? Because a liquid is just a liquid, okay? And the gas that we have has a pressure of 1 atmosphere, okay? So the value of delta G0 for the equilibrium in part A, yeah, okay, just want to make sure. So remember, we've got this expression here, delta G equals delta G0 plus the RT ln Q. Okay, but we just talked about the fact that if we have standard conditions here, that basically your delta G equals delta G0, right? Because this is 1 atmosphere of pressure, so natural log of 1. So these two are equal to one another at this point. This term just goes away, okay? So the value of delta G0 here, if this is at equilibrium, what did we say that delta G is at equilibrium? It's 0, right? Okay? So at this particular moment in time, delta G0 is actually just 0, like delta G, because these two are equal when it's under standard conditions like this. Okay? Use thermodynamic data in Appendix C and equation 19.12, 1912, to estimate the normal boiling point of CCl4. So equation 1912 is the one that you might expect here. Delta G equals delta H minus T times delta S. Okay, now how are we going to estimate the normal boiling point of CCl4 from that? Right, so that's where they're saying using the thermodynamic data in Appendix C, which I will give that to you. But there's another key piece of information here. Now, the only thing we can look up on the back of the book is the delta H0, right? Delta H at standard conditions, the delta S at standard conditions. So this delta G would be at standard conditions. That's okay here because our delta G's are equal to one another at this point. All right? What is our delta G here? It's 0, right? At equilibrium, at the normal boiling point, it's 0. So then we can rewrite this, and this was on one of our AP questions. We can rewrite it like this, right? And then if you want to go ahead and completely rearrange it before we even solve, divide both sides by the entropy change. I wanted to make a line all the way through that. So T equals delta H over delta S. Okay? So if we can figure out what our delta H and our delta S are here, then we can take, delta H divided by delta S, and that will give us the temperature at our normal boiling point. What's that? Oh, the T delta S?
Yes.
Well, okay, what I did, I didn't show this, but you've got 0 equals delta H minus T delta S, and I just took the T delta, I added the T delta S to both sides, right? So, no, it actually, both sides should be positive there. So the delta H for this one, rather than looking in the back of the book, I'm going to cheat and just look at the sample problem here. And again, it says, you know, well, never mind. I don't need to talk about that. The delta H for, I need both of these values. Where are they? Okay, I'm going to have to get them indirectly here. So the delta H of formation for CCl4, what we're going to have to do here is take the products minus the reactants, look up the delta H's of formation for each of these. Okay, so the delta H of formation for the CCl4 gas is negative 106.7. And then the delta H of formation over here, sorry, this is getting really crowded. Maybe I should take some of this out of here. Erase this, and this, and this, and see if I can do this. There we go. Okay, so the delta H of formation on, and these are all standard conditions, is negative 139.3 kilojoules per mole. Still sloppy. So that's how we'd find our delta H, right? We take the products minus the reactants, and then same thing with the delta S. You just find your S values. So the S of this one is 309.4. And the S for the CCl4 liquid is 214.4. Which, wait, that's in joules. Sorry, that's joules, not kilojoules. And it's good to look at these every once in a while just to see if they make sense. Does it make sense that there's a higher entropy for the gas than for the liquid? Yeah, that makes sense. Okay, so then you just do products minus reactants for both. So when I find my delta H here, it's going to be negative 106.7 minus a negative 139.3. And then your delta S is going to be 309.4 minus 214.4. And then what you got to watch out for here, I didn't include the units on this part, but one of these is in kilojoules, the other one's in joules, so we're going to have to convert one or the other before we find our temperature. So then you're going to end up with 32.6 kilojoules here. And then you're going to end up with 95.0 joules here. And actually this is joules per mole times Kelvin, I guess. And this is kilojoules per mole. So then we have to change one of these. It really doesn't matter which one you change at this point. So, you know, just because it's a little bit easier for me to have a bigger number here. So basically to find your T, you take 32,600 joules per mole over 95.0 joules per mole times Kelvin. See how the units kind of work out here, right? Cancel all this stuff out. You're left with 1 over 1 over K, so it ends up being K for your units. Everybody all right with that? A little weird. So then you divide those two by one another, and you should end up with 343 Kelvin. And I didn't punch that in, so I need to make sure my numbers are right. Yeah, okay, I plugged everything in right. Okay, so 343 Kelvin, which could be your answer because they don't specify what unit to put it in. They go ahead and put it back into Celsius in the problem, but you don't really need to do that. Okay? So that may have been a tiny bit of a rabbit trail. The good thing about the first part of that problem is it does show you how delta G0 and delta G can be the same in certain situations. Now we're going to look at one in the next example where they are actually different. Okay? So there's the Haber process. Calculate delta G at 298 K for a reaction mixture that consists of 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 0.5 atmospheres of NH3. So you can kind of see already this is not at standard conditions, right? So we're not talking about delta G0 at this point. We're talking about delta G. So again, my equation here, delta G equals delta G0 plus RT ln K. No, RT ln Q. Sorry, I'm getting ahead of myself here. So we're trying to find delta G. How do we find delta G0? What information would I probably need to find the delta G0 here? Well, we're going to have to figure out Q eventually, right? But I've got to figure out delta G0 also if I'm going to be able to solve for this equation, because I already have an unknown over here. I'm going to need another piece of, or some more pieces of information, potentially. What if I had a delta G of formation for the NH3? Would that work? Because I don't need the delta G of formation for these two because these are just elements, right? So these are both 0. Okay? Now, the one thing you got to watch out for here is this is the delta G of formation will give you for the formation of 1 mole of NH3. This is going to be for 2. So basically we look up the delta G of formation for 1 mole of NH3 and just multiply that by 2. Okay? And I'm just going to give you that number because I don't think we need to worry about that calculation at the moment. It's going to be negative 33.3 kilojoules per mole. Is that right? I want to make sure that, because I don't see anywhere here where they multiplied by 2, so I want to make sure that. See, I don't know what the. Okay, so NH3, let me find that real quick in Appendix C. It's going to be a boring video. Okay, yeah, it's negative 26.5. Wait. That's not right. Oh, okay, it's a gas. Negative 16.66. So, yeah, they have multiplied it by 2. All right, just wanted to make sure. So negative 33.3. That's our delta G, kilojoules per mole, plus R. Now the R that we have to use here is going to be the 8.314 because that's the one that has joules in it, right? So 8.314 joules per mole times Kelvin times our temperature, which is what here, 298. There we go. Times ln Q. Okay, now here's where we have to probably step back for just a moment and calculate the Q value so we can plug it in here. All right? How would I write the Q expression for this one? It's using the pressures, right? You can write an equilibrium expression using pressure or concentration. It's been a while since we've done one with pressure. But it's just products over reactants, right? Okay, so the pressure of the NH3, which is 0.5, squared, because there's a coefficient 2 in front of it, divided by the two reactants, which you've got N2, which is 1 atmosphere, 1.0, times H2, which is 3, and that has to be cubed, right, because there's a coefficient 3 in front of it. So then you work that out for Q, and that's going to give you 9.3 times 10 to the negative third. Ran out of room. And we still have to take the natural log of that for the equation, right? So then notice what happens to your units here. You have to be a little careful. Kelvin cancels out. There's no unit on Q. That's going to give us joules per mole here, and that's going to give us kilojoules per mole over here. So we're going to have to do some sort of conversion before we add these together. But your delta G there is negative 33.3. And let's, I'm going to keep this in kilojoules because delta G is usually reported in kilojoules. And then we'll change the other one. So you got 8.314 times 298 times the natural log of 9.3. Okay, I'm getting negative 11,589 kilojoules. So let's just go ahead and convert that into negative 11.6. I said kilojoules, I think. Sorry, that's how many joules that we had. So we'll convert that into kilojoules. Now we can add these two together because they have the same units. Okay. So our delta G for this is negative, I can do this, negative 44.9. All right. So let's step back for a second and think about what that just told us. Because again, this is all sort of related to equilibrium, right? So when well, what did I do here? I guess it's a little bit hard to tell because I kind of changed two things at the same time, but it appears that one of them I changed a little bit more than the other. I changed the pressure of the hydrogen by quite a bit, right? I greatly increased that pressure. And I decreased, well, actually, these are both going to have the same effect, right? Because at the same time, I decreased the pressure of the NH3 from standard conditions, right? So if we'd had standard conditions, these all would have been 1 atmosphere. But what I did is I increased this to 3, and I decreased this to 0.5. So I took away some of the NH3, I added some H2. Well, which way is that going to push the equilibrium? Yeah, if I add a reactant, take away a product, that's going to push the equilibrium towards the product, which would make this thing more spontaneous in the forward direction. Does that make sense? Okay. My delta G got more spontaneous or more negative when we did that. Does that make sense? More thermodynamically favorable. Thank you. Okay. Yeah, as opposed to the delta G0, which we calculated to be negative 33.3 kilojoules per mole up here. Does that make sense? Okay. So, yeah, thank you for clarifying that. So you compare those two, and you can see, okay, so my delta G under these conditions is actually more negative. So it's more thermodynamically favorable in the forward direction, which is what we would expect. This is kind of telling us which direction this thing is going to shift to get to equilibrium, right? Okay, so you can kind of see how those are related to one another. All right, at equilibrium, Q equals K, right? And so actually we can rewrite this equation here. So and delta G is equal to 0. So the equation becomes 0 equals delta G0 plus RT ln K. So you rearrange that, and you get delta G equals negative RT ln K. And then if you just don't like having that natural log expression in there, then you can rearrange that. You can E both sides, right? So you'd have to, basically you'd have to divide both sides by the negative RT first. Get rid of this on this side, then you got natural log of K. So then you E both sides of this thing. E to the natural log of K is just K. And then you have E to the power of negative g over RT. Okay, and this is the equation that's on your equation sheet, I believe. It might be, maybe it is the delta G equals negative RT ln K. I know on the old equation sheet they had both.
It's, delta G is delta H minus T times.
Okay, so that's in the thermodynamics. It might be in the equilibrium section.
No, it's there.
It's there?
Negative RT times ln K.
Okay.
Yeah. Some people say that they...
Oh, okay, so they don't have this one on there anymore?
No.
Okay. Maybe they thought that was confusing, which it can be. But I guess maybe we'll talk more about this one than this one. They're basically the same. The only time this one helps you on the bottom is if they're asking you to solve for the equilibrium constant. Then you don't have to think about e-ing things, but we can do that, right? It's just like tenning something. You just e it instead of tenning it, right? Okay. So here's an example on this one. Use standard free energies of formation to calculate the equilibrium constant K at 25 degrees Celsius for the reaction involved in the Haber process. Well, we just talked about the Haber process, so that's the N2 plus 3H2 yields 2NH3. Okay, so there's the Haber process. And we already calculated the standard free energy change for this reaction. It's negative 33.3 kilojoules per mole. And also negative 33,300 joules per mole, which could come in handy because we have R in this equation. So they're being nice here. So we are calculating equilibrium constant here, but let's practice doing that with the equation you're given on the equation sheet, okay? So anytime that you have a question about delta G and K in the same problem, the equation you're probably going to want to use for that one is the delta G0 equals negative RT ln K. All right? That's basically your equation that relates the two of those. So I should have put a 0 here, sorry. That's the standard delta G. So our delta G0 is negative 33.3 or negative 33,300, which I'm going to use this number because my R is in joules per mole, so that's going to make those two match. All right? So negative 33,300 joules per mole is equal to negative 8.314 joules per mole times Kelvin times my temperature, which is 25, so 298, K, times the natural log of K, right? That's what we've got to solve for here. So when we multiply these two things together, the K's are going to cancel out. When we divide both sides, then the joules per mole is going to cancel out, which is going to leave us unitless. Is that okay? Yeah, K is unitless, so no problems there. So I guess I'll go ahead and work this one out. Negative 8.314 times 298. Negative 33,300 divided, whoops, that was too many threes. Divided by that answer. So I'm getting 13.4 is equal to the natural log of K. But, you know, I kind of get why they give you that equation on the AP exam, because that's, once you solve all of that other stuff, it cleans it up a little bit, and this is not all that bad from that point, right? So then you just E both sides. Let me make sure that, yeah, 13.4, okay. So you E both sides, so E to the 13.4 power is equal to K. So then you just, you know, find your E button, which may be difficult to find depending on how often you use natural logs or E's. So the K on this one is going to be big. Yep. Only rounding to 1 sig fig. Rounding to 1 sig fig. I'm not exactly sure about that one. So they rounded up to 7 times 10 to the 5th for your K value. And I guess that's for the same reason that we only count the numbers after the decimal when we're doing pH. I guess that's the only thing I can think of off the top of my head here.
Or like the mole, or you went by 1 mole?
No, because I mean those canceled out, right? So the only two numbers we really have here they both have 3 sig figs in them. It's got to be because of that last decimal there. So I don't completely understand sig figs when you're dealing with natural logs or logarithms or that sort of thing. It's a little weird, but evidently you just count the one after the decimal, and that's the only one that counts. All right. So that's your answer there. So let's think about that for a second. That's a pretty large equilibrium constant, right? For this reaction, which should tell us what? The right is highly favored here, okay? Which is interesting because it doesn't really happen quite as much as you would think it would for that large equilibrium constant at that temperature. We have to do some things to help this reaction. And part of that goes back to the whole, just because it's thermodynamically favored doesn't necessarily mean that it's kinetically favored, right? So sometimes there are things we have to do to encourage these reactions to happen, even if they have very large equilibrium constants. Okay? Does that all make sense? I mean, it gets a little jumbled, like the relationship between delta G 0, and the equilibrium constant. But you just kind of have to make sure that you understand what each of those things mean in each of their contexts. All right? And that's it for this unit. So I guess we'll see you guys on Monday.